So this is the sister video to my oxidation one, which means this one is all about an easier way to remember reduction reactions. I'll follow the same format that I did in my oxidation video, which is to learn the reactions by reagent rather than functional group, because the reagents do follow some simple rules that you can apply to multiple functional groups. So this mnemonic is from Gen Chem. Leo the lion says Gur. Leo, lose electron oxidation. Gur, gain electron reduction. In Orgo, we don't really use or care about this because there's an easier way. And that's to say if something is reduced, it gains more bonds to hydrogen or fewer bonds to oxygen. It's as simple as that. Typical reducing agents that you will see have lots of hydrogen molecules in them, which make them easy to identify. If you get some reagent on the test, you have no idea what it is, but it has lots of hydrogen molecules, you should think reducing agent. So the big reducing agent you should know for the MCAT is lithium aluminum hydride, or LAH. It is a very strong reducer and works by supplying hydride ions. And the rule for LAH is that it reduces all the way to an alcohol. So a ketone will be reduced to a secondary alcohol. And I'll use the green check mark to signify those functional groups for which the rule applies. An aldehyde gets reduced to a primary alcohol, so it gets a check mark too. Now, I've put nitriles and imines in the same column here. Obviously, this is going to be an exception to the rules. There is no oxygen in these molecules. However, both nitriles and imines will be reduced to the corresponding amine. Now, what about amides? They do have oxygen, but they also have nitrogen, and they are also an exception. They too are reduced to amines. So the exceptions to our LAH rule fit in another rule themselves, which is if the compound contains nitrogen and can be reduced, it will be reduced to an amine. Esters will be reduced by LAH and two products will be formed, as the esters split more or less. Both the products will be alcohols. And finally, carboxylic acids will be reduced to primary alcohols, so they follow our rule as well. So that's LAH. If you know no other reducing agent for the MCAT, know this one. Next up we have NaBH4, sodium borohydride. Like LAH, it is a source of hydride ions, but it is a weaker reducing agent. This means it will have the same effect, follow the same rules, but it cannot reduce as many functional groups as LAH can. It will reduce a ketone to a secondary alcohol, and it will reduce an aldehyde to a primary alcohol, just like LAH does. It will also reduce imines to an amine, but it cannot reduce the higher priority functional groups. It can reduce an acyl halide, which I don't have on the chart, but this has more to do with how reactive acyl halides are than how strong of a reducing agent sodium borohydride is. Up next is catalytic hydrogenation. I have it labeled here as H2 with a palladium catalyst, but any of these metals can also be used as catalysts in addition to palladium, and they are platinum, nickel, rhodium, and ruthenium, so watch out for that on the MCAT. I would just recognize this reagent as H2 with some high atomic number transition metal. Catalytic hydrogenation is used to reduce double and triple bonds, and it will take them all the way to alkanes. So an alkene will be reduced to an alkane, which I'll signify with a red check mark, and an alkyne will also be reduced all the way to an alkane. There are some exceptions, not so much about catalytic hydrogenation, but about reducing alkynes that you should know for the MCAT, so I'll discuss them briefly now. There are ways to stop the reduction of an alkyne just at the level of alkene before it gets all the way to an alkane. The first reaction is something called Lindlar's catalyst, and produces a cis-alkene. To get the trans-alkene, you react it with sodium and liquid ammonia. And this last one isn't so much an exception, but it's not on the chart either. Benzene and its derivatives can actually be reduced at high temperature and pressure with catalytic hydrogenation, which is something you wouldn't expect given how stable benzene is. Here I have toluene being reduced to methyl cyclohexane. The wolff-kishner reduction is a rather famous one. It uses basic conditions and as a rule converts carbonyls all the way to alkanes. The reagent is hydrazine, NH2, NH2, which has a nitrogen-nitrogen bond, and the mechanism is similar to the mechanism for forming imines. The The wolff-kishner is particularly useful for reducing cyclic ketones to cycloalkanes. There are no exceptions, at least that I know of, so it will reduce a ketone all the way to an alkane, and it will also reduce an aldehyde all the way to an alkane. And finally, we have the Clemmensen reduction, which uses zinc and mercury. It accomplishes the same things as the wolff-kishner, but is acidic rather than basic. So it will reduce ketones to alkanes, and it will also reduce aldehydes to alkanes. And that's it for reducing agents, and our chart's complete. I would internalize and memorize this. It's a lot cleaner and nicer than the oxidation one, which means these reagent rules have very few exceptions, so that's nice. Here are a few questions. Pause the video while you work on them, as the answer slide will appear in about 5 seconds, so pause it now. And here are the answers. Pause the video again if you'd like to review them, and if you have any questions, leave a comment and I'll get back to you. So yeah, that was about 20 reactions, but 5 simple rules for reagents. Now you can say LAH plus oxygen equals alcohol, with nitrogen equals amine, rather than saying, okay, when I react an ester with LAH, I get, and when I react this functional group with sodium borohydride, I get, etc., etc. You just know, rather than having to recall a specific reaction. It's kind of like learning your times tables. That's it for oxidation reduction as far as orgo is concerned, and my next reaction video will be SN1, SN2.